Welcome to Safety Engineering Briefings. Short, practical insights for software and security engineers. Last year, a major airline experienced a brief but significant system outage. Flights were grounded. Passengers were delayed. The root cause? A single, seemingly minor configuration change. A developer, deploying a routine update, accidentally introduced a setting that overloaded a critical database connection pool. It wasn't a bug in the code itself. It was a mistake in how the code was used. These incidents happen far more often than we admit. They're rarely dramatic code failures. They're subtle errors in operation. We often talk about software bugs as the primary safety risk. We focus on code reviews, static analysis, and testing. These are important, but they address a specific type of failure. Human actions introduce a much wider range of potential problems. Think about it. Every deployment, every configuration change, every incident response, these are all driven by people. And people make mistakes. It's not about blaming individuals. It's about recognizing that human performance is inherently variable. We have limits to our attention, memory, and decision-making. A common misconception is that better training will solve this. Training helps, of course, but it doesn't eliminate the underlying cognitive limitations. Even the best trained engineer will eventually make an error, especially under pressure or fatigue. Another mistake is believing automation will fix everything. Automation reduces the frequency of certain errors, but it introduces new failure modes. Automated systems still require configuration, monitoring, and maintenance, all performed by humans. The key isn't to prevent all errors. That's impossible. It's to design systems that are tolerant of errors. This means building in layers of defense. Redundancy is one example. But more importantly, it means minimizing the impact of a single error. Can a single misconfiguration bring down the entire system? Or is the damage contained? We need to think about how errors propagate. A small mistake in one component shouldn't cascade into a catastrophic failure. Consider the trade-offs. More defenses add complexity. Complexity introduces new opportunities for error. The goal is to find the right balance. Let us look at a typical e-commerce platform. They use a microservices architecture with a separate service for managing product inventory. This inventory service relies on a Redis cache to quickly serve product availability data. A developer needs to update the cache and validation logic. They test it locally. It works fine. They deploy the change to production. Immediately, the website starts showing incorrect inventory levels. Customers can order products that are out of stock. What happened? The developer didn't account for a subtle race condition in the production environment. The cache and validation logic relied on a specific timing window. Under production load, that window was too small. The developer's local testing didn't replicate the production conditions. The consequence was lost revenue and customer dissatisfaction. A more robust design would have included circuit breakers to prevent cascading failures. It would have included more comprehensive integration tests that simulated production load. It would have included better monitoring to detect the issue quickly. But those defenses weren't in place. The system wasn't tolerant of the developer's error. Human error isn't a bug to be fixed. It's a fundamental characteristic of complex systems. Focus on building systems that limit the impact of those inevitable errors. Prioritize error tolerance over error prevention. Ask yourself, what single mistake could cause the most damage in my system, and what can I do to mitigate it? If this topic was useful, take a moment to reflect on how it applies to your own systems. See you in the next briefing.